Okay, so hello and welcome back. So in this video we want to do a couple of circuits related to RC and basically a couple of example circuits related to RC and RL circuits to basically to deepen our understanding of these circuits, and then after this we will get to resonant circuits. So we have a couple of circuits over here. Let's say that you have an RC circuit. So you have this circuit over here, and in this circuit you have a capacitor, and this capacitor is connected to a resistor. This resistor goes to ground, and then over here you have your V of out, and this is your V of in. Okay, so this is a capacitor 0.053 microfarad. C is equal to 0.053 microfarad, and R is equal to 4 kilo ohm, for example. So in this circuit you want to calculate a couple of things, like for example the reactance of the capacitor and the impedance of the circuit, the output voltage, the current going through the circuit, and basically theta, the phase angle, and that's basically all that you want to calculate here. Now, in order to calculate these values, so first of all you need to, in order to solve a circuit, of course you need to understand it, otherwise you will not be able to solve it. Meaning that, for example, if I want to calculate the output voltage for this circuit, it's obvious that the output voltage is the voltage across this resistor. Okay, so now that I know that the output voltage is the voltage across the resistor, now I know how to calculate the output voltage. Otherwise I couldn't possibly, for example, memorize something there are all kinds of different formulas for example, different RC circuits and different RL circuits and so on and so forth. And there are thousands of different situations, and for each kind of situation you need to change your formulas in different ways. So that way it's actually not possible to do anything in electronics, because electronics is actually vast. Wherever you go, there is something new. But if you know the basics and if you know the principles, then wherever you go, it's basically the same thing, changed a little bit, and then apply logic to any situation. You'll be able to figure out what the formula is, for example, in this particular situation. So now, for example, in this particular situation, I know that I'm calculating the voltage across this resistor. Okay, so my V of out is equal to and these circuits behave pretty much like a DC circuit. So because this is a voltage divider simply, and you have this capacitor over here, and you have this resistor over here, and this is and as you can see, this is connected to a power supply. But in this case the power supply is an AC signal, so it's pretty much like a voltage divider circuit that you use in an AC circuit over here, right? So this is your V of S. So for example, this is R1, R2, and this is a simple voltage divider circuit in DC. Now when it comes to AC, it's basically again the same principle, kind of I mean, there is a lot of similarities between these two circuits. Meaning the basic principles are the same. Meaning that if whenever you have these two resistors across a power supply, what happens is that you will have some voltage drop across these two resistors. You will have, for example, V of R1 and some voltage drop across these 2 points, which is V of R2. Okay, and in this kind of circuit, as you know, to calculate the voltage drop, for example, across this resistor or V of R1, what you do is that you have to basically take your R1 and divide it by the equivalent resistance of the whole circuit, R of EQ or R of equivalent, and then you multiply that by V of in, which is basically V of S in this case. Now I don't really know how I know this. It must be based on some other equations that I know, but basically, I mean, I personally, I don't know much in electronics, but all that I know is in electronics is based on experiment, not based on not mainly based on theory. I use theory to what I experimentally know. Otherwise, I mean, for example, I can, since I have, for example, done this circuit, for example, practically, I know that, and I have basically measured the voltages across these two resistors and the power supply and so on and so forth. I know that this kind of circuit, for example, behaves in this kind of way. And then based on that knowledge, I write these equations. Otherwise, basically that's what I do. I don't know, other people might do other things, but that's basically how I do it. But of course you will be able to find, for example, to find out where this comes if you go back into DC circuits, which we might do someday, I don't know, but for now we are not talking mainly about DC circuits. But anyway, in this circuit, if you want to calculate, for example, the voltage across this resistor, which is of course, by the way, the voltage at this point, because if you for example, if you think of this voltage over here, if you call this, for example, V of out, then that voltage, of course, and if that voltage was with reference to the ground, right? So then that would be the voltage across R1. If this was V of out, if this point was V of out, and if that voltage was reference to ground, then that would be the voltage across the two resistors, and that would be the same thing as the voltage across the power supply. But then in DC circuits, it's always possible to reference your voltages to any other point in the circuit, meaning that I can always, for example, go in this circuit, and I can always go in and say that, for example, I want to measure my voltage from this point to this point. That's possible in this circuit. Or I could go in and say that I want to measure my voltage from this point to this point. That's also possible, and that becomes, for example, V of R1 and V of R2. But that kind of thing usually we don't do in AC circuits, because AC circuits are mainly probed by oscilloscopes, and oscilloscopes have this, I mean, the whole thing is basically this, usually, I mean, in in an AC circuit, everything is basically reference to ground. You don't go and you don't usually go and basically, because it's mainly not really possible to go in and put your ground oscilloscope clip to any point that you wish in the circuit. It has to be the circuit ground. So for that basic reason, basically everything in an AC circuit is basically every voltage measurement is reference to ground. So but anyway, I'm getting off topic. Now in this particular circuit, in this DC circuit, if you want to calculate the voltage across, for example, this resistor R1, it's going to be the ratio of R1 to the equivalent resistance in this circuit, and then you multiply it by the input voltage or the supply voltage. And if you want to calculate the voltage across R2, that would be basically R2 over R of equivalent, R2 over R of equivalent times the input voltage. Okay, and then again in this circuit, for example, you have this supply voltage which is V of S, and that is equal to these two voltage drops added together, meaning that V of R1 plus V of R2 would be equal to the power supply voltage. And this is by the way also called the Kirchhoff's voltage law. Okay, now all of what I said, all of what I just said, you can, I don't know, keep it or let it go, doesn't matter, but from that, what's important is that in this circuit, basically the voltage drop, for example, across this resistor is the resistance of this resistor divided by the equivalent resistance of the whole circuit times the input voltage. And the same thing happens here as well. So these two are connected in series. One end goes to ground, one end goes to your signal, and then the voltage drop across this resistor is actually going to be equal to the value of this resistor R over the equivalent resistance in this circuit, which in AC circuits is called impedance, Z, divided by times V of in. Okay, so that's basically how I know how to write this relationship between these few things. And then what happens here is that I know the value of my resistor over here is 4 kilo. I know I can calculate my impedance over here times V of in, which is in this case 10 volts peak to peak. 10 volts peak to peak, and the frequency is 1 kilohertz. Okay, so that way I can calculate it. So now let's calculate, for example, this output voltage over here. So how can you do that? So basically your Z over here, Z basically in these RC circuits is equal to the square root of X of C squared plus R squared. Okay, so that's your Z. And X of C in these circuits, which is the reactance of this capacitor in this circuit, and reactance is basically another name for the resistance that this capacitor has in this AC circuit. So X of C squared, X of C is the same thing as 1 over 2 pi is the same thing as 1 over 2 pi FC. Okay, so this is frequency and this is the capacitance of that capacitor. So basically your x of c is equal to 1 over 2 pi fc. F, the frequency is 1 kilohertz, so it's 10 raised to the power 3 hertz, and your capacitor is 0.053 microfarad. 0.053 microfarad, so times 10 into 10 raised to the power negative 6 farad. And if you do this calculation, what you will get is, you can simplify it a little bit, so that would be 10 raised to the power negative 3. And you can use a calculator, for example, something like this. So it's equal to 1 over, it's equal to 1 over 2 pi times 0.053 into 10 times 10 raised to the power negative 3, which is equal to 3002.9. Okay, so you can do it this way, or you can basically write it approximately as 3002.9, but it's usually better to write it as basically as the fraction that you get, meaning that it's 500,000. It's exactly equal to 500,000 times over 53 pi. Over 53 pi. Okay, so you can use this value all throughout your calculation without losing the precision on your numbers, or because this number is actually the rounded version of this number. Okay, so that's basically x of c. Now, since you have calculated x of c, you can now calculate your z over here. So your z is equal to the square root of x of c squared plus r squared. So x of c was equal to this value, so 500,000, or you can write this as, you can simply write this as 5 into 10 raised to the power 5 over 53 pi. This is easier. Okay, so that's that you can write as 5 into 10 raised to the power 5 over 53 pi, and you have to square this whole thing, plus r squared, and your r is equal to 4 kilo. So that's 4 into 10 raised to the power 3 whole squared. And you want to take the square root of this whole thing. Okay, so now I use my calculator here, and that is equal to SQRT of this value, which is, that is, I use this thing over here, and that is 5 into 10 raised to the power 5 over 53 pi whole squared, plus this thing over here, and that is also whole squared, and that would be 4 into 10 raised to the power 3. Okay, so let's see. So you have, so 4 into 10 raised to the power 3 whole squared, and that is 5 into 10 raised to the power 5 over 53 pi whole squared, and that's equal to 5001.8. So it's equal to 5001.8. And the unit over here, the unit for impedance is ohm. The unit over here for x of c, or reactance, is also ohm. Okay, so now you have calculated your x of c, you have calculated your z. So then your V of out is equal to basically you're calculating the voltage drop across this resistor, so R over Z times V of in. R over Z times V of in, which is equal to, well, R was 4 kilo ohm, so 4 kilo ohm, 4 into 10 raised to the power 3 ohm, over Z was 5001.8 times V of in, and V of in was 10 volts peak to peak. So I multiplied over here times 10. So this is the same thing as 4 into 10 raised to the power 4 over 5001.8, which is equal to 4 which is equal to 4 into 10 raised to the power 4 divided by 5001.8, which is equal to 7.99. Okay, 7.99. Take it as 8. Is equal to 8 volts peak to peak. So your V of out is equal to 8 volts peak to peak. Now, so you have your V of out, you have your I, you have your theta. I'm sorry, I we have to calculate still. So it's always a good idea to keep two. Of course, I'm doing this on a computer, but it's better to write on a piece of paper. But still, on a computer you can do the same thing, meaning that you can always, for example, on a computer you can have a what do you call it, a paint, for example, sheet over here, and keep track of things over here, because things will get messy. Okay, so the things that I have calculated here are basically, first of all, x of c, which was this value over here. So x of c was equal to 5 into 10 raised to the power 5 over 53 pi, and that was equal to something about 3002.9 ohm, right? And my z was basically, you see, you just lose track of things, and your z was basically 5001.8 ohm, and your V of out was equal to 8 volts peak to peak. So now you know, basically you don't have to keep looking for things over here. And then okay, so then what you have here is, now you want to calculate the current that is going through this circuit. So now, in order to calculate the current that is going through the circuit, it's pretty much like a DC circuit, meaning that if you basically have a DC circuit over here, so let's say that you have a power supply over here. Actually, the power supply, the positive, I want it to be up. Let's say that you have a power supply over here, and here it's going to a load, and here's your V of S DC, and here your R, and there is some I going through this circuit. This is DC actually. So in this circuit you can simply use the Ohm's law. V is equal to IR, and I is equal to V to R. But basically in that circuit, instead of R, the equivalent resistance is basically Z. So in this circuit you can write I is equal to V to Z, right? Z is basically your impedance. So then you can write I is equal to V to Z, which is equal to basically the supply. This is the supply voltage, which is 10 volts peak to peak, and your Z was equal to 5001.8 ohm. And now this calculation would be 10 divided by 5001.8 is equal to 0.002, around 2 milliamp. It's equal to 0.002 amp, which is equal to 2 milliamp. So that's basically your current over there. So your I is equal to 0.002 amp, which is equal to 2 milliamp. Okay. Now the next thing that you have here is the theta. Okay, the theta, the phase angle, and the phase angle is basically the angle that there is a voltage across this resistor, which was basically 8 volts peak to peak, and there is a voltage coming in which is 10 volts peak to peak, and there is some sort of phase difference between these two voltages. And in these kinds of circuits, what happens is that if you have, let me show you what I mean by this. This is important. So in these kinds of circuits, what happens is that you have basically a capacitor over here, and this capacitor is coupled to a resistor, and this goes to ground, and then here you have your V of out, and here you have your V of in, and this is your C, this is your R, right? So this is actually an RC filter, right? Or basically, in short, it's a voltage divider. So what it does is that depending on the frequency depending on the frequency of this incoming signal, your output voltage is going to change. And how that changes is that you saw that the reactance of this capacitor X of C was equal to 1 over 2 pi of C, meaning that there is an inverse relationship between your frequency and the reactance of this capacitor, meaning that the higher your frequency, the lower your reactance, because this is in the denominator, this is in the numerator. So as you increase your frequency, the reactance of this is going to decrease. So the reactance of this the reactance of this capacitor decreases, the voltage drop across the capacitor is going to decrease. And so with that, the voltage drop across the resistor has to increase. And so what that means is that as you're increasing the frequency, the voltage drop across your resistor is increasing, which means that your output voltage is increasing, because your output voltage is actually nothing but the voltage across the resistor. So then you would have some situation like this, where you have your F of in here and V of out, and this is, by the way, also V of R, basically the voltage across the resistor. And as you increase this frequency over here, your voltage, the voltage across the resistor is going to increase, and it's going to increase up to some level very close to your supply voltage, and then it's going to level off here, and then it keeps going in that direction. So and you can see that at low frequencies over here, much of your signal is being suppressed. Much of your signal is not passing through. At higher frequencies, much of your signal is passing through. So that means that, and for this reason, this circuit has been called a high pass filter. A high pass filter. Okay, that means that at high frequencies, much of your signal is passing through. Now, now what happens here is that there is a relationship between the basically the phase angle of the voltage across this resistor and across this capacitor and across and the voltage coming in here and the current passing through the circuit and so on and so forth. And that's basically called the phasor diagram. The phasor diagram. Now the phasor diagram for these RC filters is something like this. If I'm not, I have to actually V of C, V of R, and V of E. Yes. Okay, so the phasor diagram for these circuits, you have to use a simple vector diagram, and that's actually something like this, meaning that here you have your V of R, V across the resistor, the voltage across the resistor, and here you have your V of C over here, and the current is actually along the same line here. So this is your I going through the circuit, and V of in is basically over here. Okay, so that's basically this thing over here, and this angle you can call it, for example, theta. This angle you can call it phi, for example, and of course you can see that in this phasor diagram, for example, if you were to calculate what theta is, you could write tan of theta is equal to this side over here, which is in front of the angle, opposite to adjacent. So opposite would be this angle, this length over here, which is the same thing as V of C, and adjacent is V of R. Okay, and there is two more basically useful relationships here. One of them is 1 over 2 pi FRC, and the other one is X of C to R. Okay, so you can calculate your theta using any of these relationships, whichever one fits your situation. Now in this particular situation, we already have calculated X of C and we know the value of R, so we can simply use this one over here. So basically tan of theta then tan of theta is equal to x of c to r, which is equal to 3002.9 divided by r was basically, I think, 4 kilo ohm or so. 4 kilo ohm. You don't have to write kilo ohm, so times 10 raised to the power 3 ohm. And if you give it to a calculator, it's going to give you 3002.9 divided by 4 into 10 raised to the power 3. And that's equal to 0.75. Equal to 0.75. It's actually not a good idea to do this, to write the ratio, because this is a ratio, and if you want to write the ratio, you have to write the whole thing, meaning that if you look at your calculator, you would see the ratio is 0.750725. So you would write the whole ratio in decimal form, or you would just use this ratio over here without simplifying it, because then you would lose some precision on your angle once you wanted to calculate the theta itself. So I'm going to write this as 750725. Okay, and now the theta itself is going to be equal to tan inverse of this ratio, or this ratio, which is the same thing. So the tan inverse of this ratio over here, and so that is equal to, so you can use the tan inverse function, which is right over here, and then you can use this value over here, and you see that I got the value itself, not even, well, it would have been the same thing, but you need to, but basically I mean, whenever you can, use the same ratio itself so that you don't lose much information about your angle. And now your angle is 36.89 degrees, which is basically, this becomes a 0 and 0.90, I call it 36.90. So it's equal to 36.90 degrees. That's your theta. So that's the theta is actually the angle between the voltage across the resistor and the input voltage, which is actually what we are looking for. Otherwise, if you were looking for the angle for the voltage across the capacitor, then you would have to calculate this phi over here, right? We will get to that as well. But basically your theta over here is now theta over here is equal to 36.90 degrees. Okay, so now let me check my answers here to make sure that I haven't made any mistakes or anything. Then we will go to the next example. Let me see. Well, it seems that I have made a mistake when I calculated the current going through the circuit, and I got 2 milliamps, which is not correct. Actually, the correct current going through the circuit is 2 amp, but the logic is the same here. The logic that I use, I don't know how I got it wrong. So you see, in these kinds of circuits, basically in DC circuits, V is equal to IR, and so your I is going to be equal to V divided by R. Now in AC circuits, this R is basically the impedance. So then in an AC circuit, your I is going to be V divided by Z, right? So now in this circuit, basically I is going to V was 10 volts to peak, and Z was equal to approximately 5002, which is equal to 10 divided by 5002, which is equal to 1.999. To 10 raised to the power negative 3. Okay. I think there is something. I think I'm supposed to. Let me see. Well, actually, the current that I have calculated 2 milliamp is actually correct. The answers, the key in this book probably, I mean, apparently has some problems in this part, so it's given me the current as 2 amps, which is not correct. The correct basically current is actually 2 milliamps. So this was basically one example. We have a couple more examples here. We will get to them in the next videos. Thank you.